Hello, Professor Aurelia Chenu. Did I pronounce correctly?
Yeah, that's correct.
Okay, good morning. So thank you for being with us. And let's, Professor Aurelia Chenu is from the University of Luxembourg. So welcome, Professor. You have 35 minutes, please.
Okay. So thank you to the organizer for the invitation. Thank you to all for being here. Like, I'm very sorry I couldn't make it in person. I would have loved it, but it's a bit far and a bit too much travel. So today I want to present you some work on like dynamics of noisy quantum system in general. And in doing so, we go through like quantum simulation to quantum control, and we end up in looking at quantum chaos. So this is some work that I've been doing with my research group at the University of Luxembourg. So far, the physics department is in the beautiful center of the university, the city center, and they are constructing a new site for this young university. So let me show, before I start, a bit what we do in the group. We are interested in general in any kind of like open quantum systems, so very non-stationary. And starting with some natural systems, such as the light harvesting systems, where you have like pigments that interact with a protein that is accounted for as an environment, and we can study how the excitation goes through the different pigments. And we can also look at something a bit more controlled, so such as artificial systems that are open in the sense that they interact with the environments. And in today's like quantum platforms, so either whether you look at superconducting qubits or trapped ions, that would be the artificial open system we have in mind. And I like to think of noise instead of being a drawback and something imposed on the system as a resource. And we'll see that using noise or integrating it in the simulation of the dynamics, we can do different things. We can do some quantum simulation, some quantum control, and well, I'll share a new results that's maybe not so good news, but that's very relevant in these noisy intermediate scale quantum devices. So that forms like the outline of the presentation. So where this is the very general model. I'll be more specific later. But our first starting line will always be a time-dependent Hamiltonian that is composed of some deterministic system plus some stochastic noise. So let me start with the first theme, which is quantum simulation. The idea of quantum simulation dates back to Feynman, that was thinking, well, if nature is too complex to model it, actually we can use it to engineer some evolution that we wish. So the idea is that we can engineer a Hamiltonian in a platform, let the system evolve, and then measure what would be this many body or this target quantum evolution. So with this in mind, we started doing a scheme on many body decoherence, and here is how it goes. So we start with a stochastic Hamiltonian. So this is my Hamiltonian, now a bit more specific, where I have a deterministic part, and I apply some noise through this operator chi of t on through this like stochastic function, sorry, on some operator L with some strength. What I mean so far with noise, and I won't go further in this presentation, is classical noise in the sense that the average is zero, the stochastic average is zero, and it is not correlated in time. We can do more complicated or complex form of noise, but there's already some interesting results that we can find with this classical white noise. This Hamiltonian generates is effectively a closed system, and one can write a wave function for it, or if we take the get and bra, we'll get a stochastic density metric that is stochastic but evolve according to this Hamiltonian. Now, if we look at this master equation and take the stochastic average in the same sense as taking this average here, the dynamics become effectively open, and we have here a part that is the unitary part that's dictated by the deterministic part of the stochastic Hamiltonian, and the dissipator that comes from the stochastic part. If the noise is classical white noise as described here, the dissipator takes the form of this double commutator, and basically one recovers in this master equation, one recovers the classical, the common Lindblad master equation. But there's some subtlety to it, and one thing that we can do, according to what we put on the L operator, is, for example, we can simulate, do a quantum simulation in the sense of Feynman of many-body decoherence. So here we have the same master equation, but with the dissipator. Now imagine that you take a dissipator that's k-body and a k-body operator. So for example, you have like k, this operator acts on like k spins. If you look at the chain of spin, for example, how does the dissipator look like? Well, it becomes many-body in the sense that we still have this structure of like double commutator, but unless in the case of Lindblad, where we would have only one of the sum, now we act on like particles I1 ik and I1 prime ik prime. So in the sense, we are linking through the fact that the noise is global, we are linking and adding like some interaction between the different particles. One way to look at how this changes the dynamic is through the fidelity that is here written for an initial pure state for simplicity. And if we do a short-term expansion, one can use this fidelity to define the decoherence time. And with this scheme, we find that it scales polynomially with the number of like particle on which we act the operators. So it's very fast decoherent. Let me show you how in some system that can create some long-range interactions. So for example, if we take Bose-Hubbard model with a lattice of trapped particle that would interact on site with some potential. Now imagine that you make this potential stochastic. So you would change it and apply some stochastic, some fluctuation on it, for example, tuning it with Feshbach resonance. What happens is that this operator then is what enters in the dissipator. And we see here that we start having some interaction between any sites n, I, to any sites j. So we create long range or like full, like we create a dissipator that interacts at any range. And again, this is due to the fact that the noise that we apply is global. So any particle I starts to interact through this particle j because through like the noise that is applied in addition on the system. So this is one first idea for application. Another possible application would be you looking at an Ising chain. And for example, if we add some stochasticity on the coupling constant J between like two sides. So now I'm making my J stochastic in the sense that I add like some classical noise. The dissipator become many-body in the sense that I have now like four spins that are interacting through this. How it changes the dynamics, looking at the fidelity that was just presenting as function of time. This is for a chain of n equal 3. Without noise, we have like some quite fast decay of the fidelity to some steady state. If we add some noise, what happens is that we see the recurrence of quantum dynamics. And even as we increase the number of sites to n equal 5, we see still some quantum recurrence. So the idea here is that the noise that we have applied on the system can actually protect some quantum features and change the dynamics. So this is one first application of this model of stochastic dynamics. Now I want to show another application, which is on quantum control. So, and this is in the frame of like shortcut to adiabaticity. So this picture, it's taken from like Tommaso Calaco, who how to describe quantum control. It would be that you have a train vector that goes through like a target trajectory so that you can create a state in arbitrary time that reproduces the adiabatic trajectory. So the goal is to turn a slow process or adiabatic process into an arbitrarily fast one. And how one can do this, for example, is going from an equilibrium state to an equilibrium state. So we want to mimic the adiabatic transport, but in a fast time. So if you have non-adiabaticity, you will create some excitation, and we want to reproduce these adiabatic transport. And one technique is the counter-diabatic transport. So I won't go very much into the detail. This has been very much developed in the case of like closed quantum system that evolved unitarily. Let me just quickly sketch the theoretical development. So consider that you have a time-dependent Hamiltonian for which you know the instantaneous diagonalization. Then one can write the adiabatic approximation as you can read here. And the question is, can we find a Hamiltonian h of t for which this state, the adiabatic solution, is exact and not anymore an approximation? So I want to find h of t such that psi n of t is the solution of this evolution. This was answered by Demir, Plack, and Rice, and later independently by Berry. And the answer is yes. This control Hamiltonian actually takes into account the original one and some correction that kill the excitations that are produced by going faster than adiabaticity. So this is known as well as parallel transport, where each eigenvalue stays on its each eigenstate is transport from one system Hamiltonian to the other, and that's the exact form of this Hamiltonian. So these techniques known within the shortcut to adiabaticity as known as the counter-diabatic driving, and they've been very successful, and they've been implemented in the lab, first in single particle, then in a BEC, where the BEC could be controlled and stayed in the ground state, so there was no like briefing mode to it. Then later on, it was done in more like many-body system, and we did some implementation of it in the unitary Fermi gas, so strongly interacting many-body system, where we implemented like compression and decompression of the trap. So here, this theory is very valid and has been very much looked forward for, investigated in closed system. Now the question is, can we extend shortcut to adiabaticity to open systems? This question was first looked at like earlier on, almost a decade ago, in the group of Vlachov-Vedral, and they had a proposal that was very much theoretical, looking at the notion of adiabaticity in Liouville superspace. Then a couple of years ago, various group, so that's the group from Brony Kozlov and Anusha Chandra at the BU with Polkovnikov also looked at it, and we looked at it at the control of a specific harmonic oscillator, and if we could do fast thermalization of a harmonic oscillator. I will show you the results in detail for this scheme. Before I do so, let me mention that we did like a case for the general setup where we can control any arbitrary open dynamics and create this dissipator that comes from the fact that it's open from two different point approaches, one being like a non-emission approach and another being a non-Markovian Lindblad master equation. But for let me not go into this general scheme for which you can find the details here. And let me present a specific case where we want to do fast cooling or fast heating of a harmonic oscillator. So the setup is that we have a driven harmonic trap with a time-dependent frequency. And we want to go from one thermal state to another thermal state, being able to change the frequency of the trap and the temperature of the system. If there is no entropy production during the dynamics, there's only a very restricted set of frequency and temperature that one can reach. And here is a representation as function of like the states that can be at reach. So as function of the inverse final temperature and initial temperature, and this is the ratio of final frequency of the initial frequency. If there is no production of entropy during the scheme, one could reach only the sets that would lie on this line. And the question is, how can we reach fast cooling or fast heating? So we came up with a scheme. It's not the only one. That's the one that we think can be easily implemented in the lab, where we use a stochastic Hamiltonian that has the time-dependent harmonic trap and to which we add noise. Sorry, this is eta t now. That was my chi of t. We added the noise on the position of the harmonic trap. If we look at this stochastic Hamiltonian and we look at the dynamics it generates after averaging over like the noise, we find an effective density matrix that is open and that follows the evolution as such. Where here we have the x term because we are applying noise on x. So these master equation can actually be used for the purpose that we were mentioning. And let me just mention one way that one can think of like this implementation is twofold. The first one being through continuous measurement in the x position and post-selection. So that would create this kind of master equation. And the second way is if we apply a noise on the position of the harmonic oscillator. So shaking the harmonic oscillator with some strength, and one would reach this master equation. So how does that work in practice? Imagine that you have a target scheme where in finite time you want to change the frequency. So let's say you want to do some compression of your trap, and the adiabatic trajectory would be given by this. Now we want to do it in a time that is faster than the adiabatic trajectory, and that's arbitrary. If we don't allow for the system to be open, what will happen is that even if we start in some initial thermal states, we will finish in some arbitrary final state that is not thermal because we need to rearrange the population of each of the eigenstates in order to reach final Gibbs state. So for it to be thermal, we can actually find a scheme where we know what is the frequency that should be implemented in the lab. So that's the control frequency, which depends on the original one, according to which schemes you want to do, like the compression here, and the correction. And it's very interesting to see that the correction here in eta t double dot of eta t is actually, it looks like what you would have from like the closed dynamics, in the sense that this ratio of frequency square root of omega 0 over omega t tilt is the adiabatic scaling factor, and this is what you would find is the scheme is closed. Now, because we allow the scheme to be open and we allow for change of temperature, we have a correction, and this correction really depends on this factor epsilon that takes into account the original trap frequency and the change of temperature. So this is the first thing, how the scheme changes from like open to from closed to open, in the sense that the correction factor here has some term that accounts for the temperature. And the second thing is that we need to add like a dephasing term. So this is the one that I had in here. So now we need to specify this gamma t, and which is basically the strength at which you will be like shaking the trap. And for which for this one we can also find the general form here, and it also depends on the fact, reflect the fact that we are making the system open. So by doing so, one can reach like the states that lie on these maps, so that represent like fast heating, or if gamma t is negative, one can reach the fast cooling of this harmonic trap. So now let me go to the last part of this presentation, which is on more relevant to the NISC area. So far, we have looked at how a stochastic Hamiltonian influences the dynamics of the density matrix. And now I'm going to ask the question, what happens to any operator? So not just the density matrix, but any operator A, how does it evolve with this stochastic dynamic? So here again, I have my stochastic Hamiltonian, to which I have like, I apply noise on this operator L. And now, instead of looking at the density matrix, I decide to look at some observable A that will evolve with this, and I look at it in the Heisenberg picture. So we can look at the equation of motion for this operator average over the noise. So this is an average over the stochastic field. This is still an operator. And here again, we find this structure of double commutator. So let me represent a bit what that would like in the space of operator. I'm starting at time equals 0 in A0. I do the experiments many times. For each time, there's one realization of the noise, and the average is given, is reproducing Lindblad master equation. Now, the question is, how does this operator deviate from the dynamics which we wish to reproduce, which would be this Lindblad master equation? So we introduced the stochastic operator variance, here represented in red, which measures the variance of this operator. So again, this is an operator, and we can solve the dynamics. And it is actually unobservable, and it characterizes the fluctuation of noisy trajectory, saying how much we deviate from the average Lindblad master equation. And we can show that it's positive semi-definite. So this variance, there's one way that looking at how it evolves, we can think of an interpretation in a bipartite system that would be as follows. Imagine that you have a bipartite system, and in the first case, you first couple the two operator A in each of the system, and you couple this bipartite system to a single path and let it evolve. That's like the Liouvillean superoperator. I'm acting on this A squared. So that's the first scenario. The second one would be that in each of the system, you look at A, and individually they would interact with their own path. And because this operator variance is positive semi-definite, we know that these term would be larger than these. So you have, in a sense, kind of like more decoherence if you evolve with a single path than if each of them have their own path. So that's a possible interpretation of it. I think it's an important tool by itself, just for characterization of a noisy dynamics. And one surprising, one relation that we found that we find surprising is how it links to chaos dynamics. So before I present this relation, I need to do present some measure of chaos and these through this out of time order correlator, OTOC, which is defined as the trace of these commutators. So take two non-commuting operators. In the Heisenberg picture, you will have like some terms that are y0xt, y0xt. So they are out of time order. And if your system has any scrambling, these correlator actually evolve exponentially. So as function of time, you will find some exponential behavior up to some saturation that happen at the reference time. So this is a measure of scrambling of information that is being used to characterize quantum chaos. And if you want to measure it, well, typically one would need to flip the sign of the Hamiltonian in order to reproduce these out of time order terms. The reason I'm introducing this term here is because the stochastic operator variance that we find actually relates to that operator. And here it's how it goes. So I showed you the evolution of this variance, which is still an operator, which is made an average over the stochastic noise. If we look at how it evolves, we find a term that has this out of order correlator. So if we take the expectation, the quantum mechanical expectation value of this evolution over a completely mixed state, so here I'm tracing over identity over n, well, we find exactly this OTOC that I was presenting with these two operators. So it means that this stochastic operator variance, once we project it on the identity, it gives a measure of the OTOC. So there's quite some subtlety that goes in. The one being that the OTOC is for like dissipative dynamics. So there's a bit different from the one in unitary dynamics in the sense that at least there's like two exponential behavior in the decay. But let me show some example of how we would use this observable to characterize a stochastic system. The model that we chose is the Lipkin-Meshkov-Glick model. So these are this is a spins that are all connected, and we look at a global spin as set with omega measuring the strength, the frequency of the two-level system in the scale of the coupling. And now we make it dissipative and stochastic in the sense that we add the noise in H0 in the system itself. So this is effectively adding, this is generating dynamics and the master equation that has like energy dephasing. So we can extract this correlator, the OTOC, as function of gamma t here, and we find these these two exponentials that are shown here for different parameters of gamma. That would be the first exponential decay here in dashed line, then followed by the second exponential decay. One interesting thing is that we can also look at the eigenvalue of this stochastic operator variance and how it evolves as function of time. And this can be a nice tool to identify what is the initial states that will evolve with the least variance at long time. So this is represented here. We have all the different eigenvalues. And here, this black line, we start in an initial state, which minimizes at long time the variance to the average dynamics, which is our target Lindblad master equation. So these are the results for the quantum stochastic LMT. We looked at the classical one. So the classical is like a harmonic oscillator that has like a phase transition according to the parameter omega. It goes from a double well to a single well. And now we make it stochastic in the sense that we again add noise to this same Hamiltonian. So without noise, this system is known to exhibit scrambling in the double well phase. If we look at the Lyapunov exponent as function of omega, we see that here it is like non-zero. Oh, sorry. So there was some mistake in the export of the PDF, but let me just say that as we increase the level of the noise or we add some noise, what happens is that this phase starts to be to so this phase starts to stabilize in the sense that here I would have a lower Lyapunov, and this stable phase starts to be unstable and exhibit chaos, where I would have like a positive Lyapunov exponent. This is actually still shown here. So as we add here a bit of disorder, we start seeing on the sorry, we start saying like that this what was chaotic stabilizes. This is a negative Lyapunov, and what was stable, so here we had zero, starts to diverge with a positive Lyapunov, and this is as a function of the increase of the noise. So through using this stochastic operator variance, we can extract the Lyapunov exponent, and for this specific model, we can actually draw a phase diagram of how the noise influences the scrambling property of the model. So with this, I think that I come to my conclusion. So let me just thanks the people that have done the work. So most of the work have been done in collaboration with Adolfo del Campo. We worked with Leonce Debay and Inigo Ingusquesa on the control of the harmonic oscillator, and with Sahara Ripur and Ali Rashakani on the development of shortcut adiabaticity in open system. And Adit Rakundo and Pablo Martinez Ascona have been looking at how it looked like for at the evolution of any operator. So with this, let me show you the final take-home message. So we always started with a stochastic stochastic Hamiltonian that's and look at we characterize the effect of noise. Looking at the density matrix, we see that we can actually use this noisy Hamiltonian to engineer many-body and long-range interactions. So that's a control of the environment in a sense. We can actually engineer a scheme where we can do control of an open quantum system. Here we looked at the specific thermalization of a harmonic oscillator, and expanding the states that the operator that we look at, and looking at any operator, we find actually we could characterize the deviation to the average dynamics through this stochastic operator variance, and we've seen how it relates to the auto and quantum features. So with this is the end of my presentation. And if you have any question, I'll be very happy to try to give you any answer. And I thank you for your attention.
Thank you, Professor Aurelia, for the very beautiful talk. So, questions? If not, I have a question myself. I was very curious about the possibility of using your model to free particles. Is that possible? Can we recover quantum Brownian motion and diffusion with this model of a classical noise Hamiltonian?
Yes, I guess yes. It would all depend on the level of how you would like model the noise. So one thing that I have not shown, but that we're looking at, is how we can we can create non-Markovian dynamics, because so far everything is Lindblad master equation that is like Markovian. But if you do like noise that has any correlation in time, or you have like a kernel that describes your noise, you start being able to do like some non-Markovian features. So that would be some extension for later on.
Okay, and then is it important if the particle is coupled with X or with momentum, for instance, can we uh, have a noise that is proportional to momentum, for example?
So in theory, yes. Then experimentally, I'm not sure. It's much more tricky, like to engineer. So the scheme that we did, like for this harmonic oscillator, we think that it's. I mean, from a theoretical point of view, it can be implemented easily in the lab. If you want to couple it on momentum, we can on paper characterize it. Experimentally, I'm not sure how that would be feasible.
I was thinking about some collision models, things like that.
Well, then you would need like to this you would need to have like some control on it, right? So I'm not sure that would be feasible. Yeah, uh, I'm not sure how you would realize this.
Okay, maybe I'll send you some emails to ask
If you
you.
have idea, that's very interesting because that's. I mean, we are a bit restricted in what we can try to apply in the lab, but yeah. So I'd be
Okay,
interested to see have your thoughts.
thank you very much. Any other question? So let's thank the speaker again. Thank you very much, Mr.
Thank you.
Professor.